Hello, everyone. Welcome to the presentation, and thank you for attending. I'd just like to start with two quick questions, please. The first one is, how many of you are actually using HTTP2 in the day-to-day lives? Okay, and the second one is just so I know how many of you have actually spent some time with the RFC and got to implement H2 in, some kind of a context. Okay, cool, thank you. So my name is Elad Shuster. I'm a senior security researcher at Akamai at the threat research team. And actually, I love security, big data, and that's a cool combination for that job title. And single malt whiskey, so feel free to approach me afterwards. What we're going to do today is we're going to sift through some of the data collection methods for the research that we've created and display, and I'll show you the research data corpus. And then we're going to go and go over some definitions about basic client fingerprinting, passive client fingerprinting, and some obfuscation methods. And at the end, we'll do some common ground about H2 and cover the fingerprint. Quick acknowledgement before I start, there were two other researchers working on this project with me. It's Ori Segel and Aaron Friedman. So I'll start with the data collection, since the data is actually the key component of every research and really connects to how broad is your visibility and how does it really reflect things going on in the real world. And so our data for the research was collected over Akamai's platform. Those of you who do not know Akamai, it's one of the leading CDNs today, and it's widely dispersed. We're about one hop away from 90% of all internet users, and I've thrown in just some numbers so you get a feel of what was this research based on. Latest statistics show that we serve about 15 to 30% of all web traffic, and you can get the magnitude of 1 billion unique IPs quarterly and 3 trillion hits per day, and that's of course for HTTP1 and HTTP2 traffic altogether. And at the time of the research, which was early 2017, this was the state of the statistics for H2 that we've seen. It was approximately 10% of the traffic that we've seen, 1 billion requests per day. We've seen approximately 30 million IPs using it, and thousands of hosts, and almost more than 500,000 user agents using it. But for this presentation, I wanted to bring some more updated data. It's been more than a year ever since. And actually, the data is astounding. It's been more than 50% increase in overall traffic, twice the number of IPs and hosts using it, and that's really, I think it's really something to be glad about, because it's an amazing technology. Though the protocol can be transmitted both over clear text and over an encrypted channel, most of the implementations actually go over TLS. So it would be also interesting to observe the increase in the usage of HTTP2. And if we look at how much HTTP2 Akamai serves out of the total HTTPS traffic, then the number always jumps higher to 30%. And I've brought this graph which shows the daily new HTTP2 connections, and you see this ramp up when a couple of our big customers decided to go to H2, and you just see a lot of connections. Today we are seeing about 120 million new HTTP2 connections on a daily basis. So the data corpus for this research was 10 million HTTP2 connections, which included about 40,000 different user agents. And they covered about hundreds of HTTP2 implementations. Those would be of major browsers or all kinds of automation libraries. Now, from a security standpoint, one of the things that we try to monitor in Akamai is web attacks over the traffic. And surprisingly so, about HTTP2, even though we see an increase in traffic and quite a lot of traffic, there aren't that much a lot of web attacks. And this arises the question of why. Why is that the case? Well, there are a couple of reasons for that. First of all, most of the tools of the trade, tools on this list, which most of you probably use on some of them on a daily basis, like Burp, Zap, Fiddler, SQL Map, Sentry MBA, Hydra, if you're into credential abuse, just don't support H2. They lack the support. And why? And a couple of reasons for that. First of all, there's not enough incentive. Most of the web servers today support both HTTP1.x and HTTP2, so why put on the effort? I mean, they would get some benefits on performance, but I don't think that's one of the major key assets that attackers are looking for. And the second point is that if you would look for automation libraries for HTTP2, you would find a few in several languages. They are mostly new and not mature enough. So just the cost of porting all of your existing tools into H2 just exceeds the gains for attackers. This is what I think, at least. And the second thing to note is that ever since the protocol was published in 2015, there aren't really flaws that were found within the protocols itself. There was a cool research done by Imperva researchers in 2016, which found some flaws in the ways that server implement the protocol, especially around the areas of handling the header compression and the stream management, but those are not flaws within the protocol itself. So there are no known flaws today, and that could be another reason for the lack of attacks in H2. And the last thing I'd like to cover before we dive into the fingerprint itself is the notion of passive client fingerprinting. And first of all, as the name suggests, passive means that we do not run or execute anything on the client side. We merely observe his behavior, and from his behavior, we try to figure out what kind of constant, unique behaviors we can derive that would differentiate him from other clients. Now, fingerprinting can be done not only on the application layer, but on the other layers as the transport layer for TCP fingerprinting, and of course the session layer, but a combination would be best. Another thing to note is that we're not trying to fingerprint end users. We are merely trying to fingerprint the way that software, that client software instances is implementing the protocol. So that there would not be any confusion there. And we do that to try and validate the client assertions. I have some use cases later on, but if the client puts on some assertions, fingerprinting could help us validate them or detect impersonators. Sorry. So for the H2 passive client fingerprinting, we actually observe the client's behavior while establishing an HTTP2 connection. We would look exactly at how the client would do his flow management. What are the default values? We would look at how does he handle the headers in terms of order, the connection settings and stuff like that. I'll go into detail just in a few slides. Now, like any other protocol, what I've said up till now is that should you choose to use it, there are some implications. By default, if you try to use it, you would be exposing some of the characteristics of your software clients. And some of you might not be interested in doing that. So there comes the question of how do we obfuscate ourselves in light of that. And so first of all, anonymity networks are not a good solution for that. Tor and I2P do not support H2. This is an interesting topic. You can look it up. There are 2 bug trackers. I'm assuming they would support H2, and each for its own reasons. And currently, it's not a good solution. But any other possible solutions are, first of all, develop your own H2 implementation. This is not as hard as it sounds, but when you are doing that, make sure that you are randomizing your behaviors. Because if I observe you as a client and I don't see any consistent behaviors, it's hard for me to distinguish you from other clients. The second solution, which requires less effort, but still it would come up on a fingerprinting effort, was the usage of a proxy. Yeah, there are 2 proxies today, MITM proxy and HA proxy, that support H2. And there's a nice node library called Node HTTP2 proxy that could be used for that. Of course, if you're using some kind of open source software, you can try and modify and recompile it. But so let's set some common grounds about H2 before we go into the fingerprint, so we'll all be on the same terms. So HTTP2 is based on a protocol that was developed by Google in 2012 called Speedy, and it was formally published during 2015. It was published in 2 RFCs. The first of them actually detailed the protocol, and the second one was related to the header compression mechanisms. I think that if you look at the internet ecosystem today, all of the major players, which is major client version, major server versions, and all the major CDNs support H2, which is a good step going forward. HTTP2 is a binary protocol. It's not a text-based protocol as you are used to seeing in HTTP1. And I'll show some example of that in a few slides. It could be transmitted either over clear text or over an encrypted channel. And the main motivation behind it is trying to address some key challenges, mainly around performance in HTTP 1.1. So the challenges in HTTP 1 are essentially, the first one is concurrency. If you want to achieve concurrency, and this is what the browsers are doing today in HTTP 1.x, you actually open multiple TCP connections, and that's not a good practice. It's not really efficient. Each TCP connection has an overhead, a performance overhead. It's called a mechanism called slow start, where the sending of packets would start slow and increase gradually until it encounters a loss. And if you do that over multiple TCP connections, which keep opening and closing, that's not a very efficient way of doing things. Version 1.1 of the protocol actually did introduce a notion of called pipelining, where on the same TCP connection you can try and resolve several requests, but it was not efficient enough, and it suffered from a phenomena called head of line blocking, where a big request would block all the others in the line. So it was not a good solution. Now, I imagine most of you have seen an HTTP request somewhere along your career, and you have the header section of that request, and you would notice that first, headers are very verbose, and they are repetitive. They keep going back and forth for each request and each response, sometimes with constant values, and that's ideal for compression. But the first versions of the protocol did not introduce any notion of compression, so that was the second issue. Now, last one is the concept of a passive server. In HTTP 1.x, unless the client requested a resource from the server could not initiate a response back to the client. And you might ask yourself, why would I want the server start to proactively push stuff to me? And the reason is that there are situations where the server can estimate with high probability that the client is actually going to request the resource. For example, if I'm downloading the HTML file of a web page and I'm rendering it, it would be very likely that my next request would be for the for static content, things like images, the JavaScript, and the CSS. So why wait for the client to download the HTML and then start sending in the request if we can just, ahead of time, send them, and with high probability would need them. So now enters HTTP 2. For the concurrency problem, HTTP 2 is using a single TCP connection. Everything is done in a single constant TCP connection, and multiple requests and responses are interleaved on that TCP connection. Header compression was addressed with the HPAC RFC, which was released along with the protocol RFC, which allows efficient coding of those headers. And last but not least, the server push was introduced, and now the server can actually push ahead of time things for the client. He actually creates pseudo requests by the client and just sends things to the client. Now, if any of you does not feel comfortable with this notion that the server is just pushing stuff to a client that you haven't requested, there's a mechanism in the protocol to opt out. By default, it's opt-in, but within the establishment of the connection, the client can opt out of it. So these are the key elements of the protocol, and the first two is the ones that we need to understand best. Frame is the smallest unit of communication. There are 10 types of frames: header frames, data frames, priority frames, ping frame, and those are the smallest units of communications. Now, since we have a single TCP connection and multiple requests and responses and some flow control frames going back and forth, there's had to be some kind of a system to organize that, and that is streams. Streams, you can think of them as a logical conversation, as channels, in which there is a bidirectional flow of frames. Each stream is allocated with a stream ID. This is like the TCP connection. And streams are numbered going from 0 and up. where the stream 0 is a reserved stream for settings, for the connection level settings, things that control the TCP connection, the window size, the settings, the maximum concurrent streams that each endpoint is willing to handle at any given moment. And from one up, we start building up the streams where, according to the RFC, oddly numbered streams represent streams which were initiated by the client, and the even numbered streams are streams that were conversations that were initiated by the server, meaning server pushes. So if we look, for example, at stream 93, we would see frames going back and forth. Each frame would have a notation. It would include metadata as for the actual stream which it's relevant for. And that way the recipient can actually go and take all those frames he's getting at once and sort them out and then forward the information to the application. The last entity which is quite trivial is message. If you think about HTTP 1.1, a request could have two sections. It could have a header section and a body, same as a response. And those two would be the request or the response. So we have the same situation in HTTP2. We can have a headers frame and a data frame, and both would be mapped logically to a message that could be either a request or a response. So that's how things actually look. We get all kinds of frames from all kinds of streams all together on a same single TCP connection, no more multiple TCP connections, and each endpoint, receiving end, can sort them out and bring them to the application. Now, the RFC defines 10 types of frames. Mostly the names are self-explanatory, but we can divide them into 3 logical groups. First of all are the frames that deal with the actual messaging. We have a headers frame and a data frame and continuation frame for that. And the second group is controlling the flow of the connection. Things like the Windows update, just as we have in TCP, the settings frame, which actually allows each endpoint to convey parameters such as what is the maximum frame size it's willing to accept, or what is the maximum header table list, or things like that. And the last group is dealing with stream management. When we have all those streams which are getting opened and sometimes closed, you need some kind of flow control mechanism for that. Now, I've mentioned that the HTTP2 is a binary protocol. It's no longer going over the wire just as ASCII text messaging. And for those of you who did not work with binary protocols, this is a bit of a taste. Each frame has a predetermined structure where the first 24 bits would denote the length of the payload. Then the next 8 bits would be declaring the type of this frame. We have another 8 bits reserved for the flags, one reserved bit which was not allocated with any meaning semantics in the RFC, and the stream identifier. As I've said, we have 31 bits for the stream identifier. That's a huge space. Next would follow the payload. And this is an example for a headers frame whose type is, here in X notation is 1. And we have some flags which denoting that this is the end of the headers and things like that, and the stream identifier. And what I'd like you to look is inside the payload, we have the first field which is called pad length. And that is interesting because padding is a notion that was introduced into the RFC to actually allow for obfuscation, to avoid the situations where the size of the payload could actually be determined, and you can pad it in different lengths, and so an observer would not actually know what the actual payload length. So I invite all of you, you can Google it up. It's called a nice page by Akamai called Akamai HTTP2 demo, where you see the same picture being loaded first by HTTP 1.1 and then by HTTP 2. And then you get some metrics about how more efficient it was. When I recorded this screenshot, it was done via VPN, so all I got is a bit more than twice 2 on performance. But I imagine that if you would do that, you would get up to 3 times, 4 times, and maybe even 5 times faster performance on that. I tried to show it in a video, but usually the refresh rate of the projectors is not high enough to show it. And the last thing we are going to cover before we actually dive into the fingerprint is the flow of the H2 conversation. And that's very important because the fingerprint really focuses on that stage of the HTTP2 conversation. As I've mentioned, HTTP2 can be delivered either over clear text, which is usually not the case, or over an encrypted channel over TLS. And when the RFC was composed, the authors wanted to rely on the existing infrastructure and not start making modification to any other underlying layers. So for the negotiation of HTTP2 over TLS is done via a TLS extension called the Application Level Protocol Negotiation, ALPN extension, where in the TLS handshake, the client adds the H2, its two characters to the ALPN extension, and if the server supports H2, they would then negotiate this protocol, and from that point on, we talk with H2. If the negotiation is done over clear text, by the way, it's done via an upgrade header, a regular HTTP 1.x header, and an upgrade header. So once the protocol was negotiated, next comes exchange of settings. Now, the RFC mandates that both sides, not only the client or the server, both sides must send a settings frame as the first frame of each connection. It could be an empty settings frame, but a settings frame has to be sent by both endpoints after each connection. And within those settings, and we'll touch upon that settings frame a bit later, but then once those were exchanged, and they are always exchanged over the reserved stream ID 0, then we can go on and start making requests. Now, if you can see in this example, in the last line of the, it's fourth line from the end, we see those are server logs. So if you see received, those are frames which were received by the server. So now the server receives a headers frame from the client, just as it would in HTTP 1 GET request, which would contain only headers and no data most of the time. And this is going over stream ID 1. And next, the server will actually respond over stream ID 1. And if the response has a body, it would be two frames, a headers frame and a data frames. So two more snippets of the log just to get you a bit more familiarized with them. You can see in the logs that the server is sending a settings frame over stream ID 0, and he's making sure that the client knows that he can handle no more than 100 concurrent streams. And then the client is responding with the settings frame on the same stream ID and sends 3 different settings about the header table size and the initial window size and so on and so forth. Once again, here we see packets frames going over stream ID 15 and a headers frame and the window update frame, which updates the initial window that was set in the settings frame, and the server responds with a headers frame on the same stream ID. So I'm summing it up. Those are the key differences between the two protocols. The 1.x versions are text-based, where the second one is a binary protocol. Both could be transmitted over clear text or over an encrypted channel, whereas in the first versions, concurrency was achieved by multiple TCP connection. In the second version, we have single TCP connection, and requests are interleaved via frames and streams. And 2 new mechanisms that were introduced is the header compression and the server push. So now for the actual fingerprinting. So of those 10 frame types for the RFC, we would be only using 4. And there are several reasons for that. First of all, not all frame types are present during the entire conversation. And in passive fingerprinting, we want to fingerprint the client as fast as we can. And we want to try and do that by looking at reliable behavior. And those 4 frame types actually reflected that during our research. First one is a setting frame. And as I've mentioned, it's conveyed configuration parameters. And the great thing from a fingerprinting point of view is that both ends must send it. So it would always be present at the start of each HTTP2 connection. And even if it's present as an empty one, that's a signal for us as the one who's trying to fingerprint the client, the behavior of that client. So the RFC defines 6 types of settings. We won't go into them. They are quite really self-explanatory. But what is important to know that each has its own representation, a hex representation. And when we actually look at the logs, and this is from Firefox 55, every time that Firefox 55 over Mac OS X is starting an HTTP2 connection, he would send those exact 3 parameters, exact 3 settings with those values. It's constant. And if we move over to Safari, Safari would use other 2 settings with, again, repetitive default values, opting out of the enable push and the max concurrent streams. And those are examples for Edge and for Chrome on Android. And if we go and just put it in a table, then we can start differentiating between different clients, only based on the settings alone. So we had a table for about 40,000 entries of those. I can't say that we were able to distinguish 40,000 user agents, far from that. There were clustering around several settings of a lot of user agents. But I think that's a good starting point for start forging the actual fingerprint. So what we propose is actually taking the hex notation of the type of the settings and concatenating it with the default value which is sent. This is for Edge. And we can see this exact example for Firefox 55. But as I've said, that was not enough. We had to gain more entropy. We needed some, to break down those clusters, so we moved on to the next type of frame. Now, Windows Update Frame is a flow management, flow control frame, and it could be sent at any point of the connection. It could be sent for the entire connection where someone would, one endpoint would like to adjust the window size for the entire connection or for a given stream. And what was interesting about it is that we noticed that some clients, when they establish a new HTTP2 connection, actually send 2 frames. They send the settings frame, which they are mandated to send by the RFC, and right after it, they would send a Windows Update frame. And this is a consistent behavior, though it's not mandated by nothing, it's just a consistent behavior. So you can see from Chrome 60 on my Pixel XL, it would send the settings frame and right after it, the Windows Update value, and the value is constant. So we just collected that value, and in the case where it would not send that, that frame, we would just put 0 there instead. And that's great. We gained some more entropy and we've broken down the cluster, but still it was not enough. So this is a chance to learn about a new cool mechanism, HTTP2, which is priority. Now, priority is a bit of a weird thing. The RFC allows an endpoint, the client, to express his preferences to the server of priorities. So it's obvious that if the server can, he should send everything he has on all the open streams and just communicate with the client. But if the server has a resource allocation problem, then the client can express his preferences to the server. Like in this example, he would say, first, please send everything you have on stream D. Once you're done with stream D, which is the parent stream, please go to stream E and stream C. You have those weights, those numbers, which are 8 and 8, which mean 50%, allocate 50% of your available resources to stream E and then to stream C. And once you're done with C, only then go to stream A and B. That's something which is allowed by the RFC, and you can see like for A and B, it would be 25% and 75%. And the weird thing is that there are no guarantees. The server does not have to respect that. I'm quoting from the actual RFC. It's only a suggestion. And you might ask yourself, why is that relevant for the fingerprint? Well, just as the update frame goes, it seems that some clients actually send 3 types of frames at every HTTP2 connection. And this is the case for Firefox, where he would send the settings frame, he would send the Windows Update frame, and immediately after he would send 6 priority frames, creating this structure that you see. This is not only for Firefox 54 or 55, it's present up until the latest version of Firefox. And you might ask yourself, why would he do that? The answer I came up with, it's like having 3 types of channels, a channel for high priority, a low priority, and a medium priority channel. but that's consistent, and we actually collect that. We collect that data, and it helps us to break down the entropy of the fingerprint even further. Just so you know, it's not something which is arbitrary. This is actually a snippet from the comments from the Firefox source code. This is hard-coded into Firefox, the exact order of these priority frames. So this is a consistent behavior. So this is all we've got up until now. We have three elements. We have the settings frame, we have the Windows Update frame, and we have the priority which we collect if the client actually sends them. And you would see we can already distinguish between Chrome and an OKHTTP library, and Curl version 754, which is the version that supports H2, and NGHTTP, and that was really cool. But we tried one last thing and to gain that entropy, and that is the last element that we are going to talk about, and that's pseudo headers. On the left, you can see a regular HTTP request 1.1 with the headers and the first starting line. And the starting line of HTTP 1.1 actually conveys some information such as the method, the path to the resource, and the protocol versions. So to replace that, the RFC is defining an entity called pseudo headers. There is one for a response pseudo header and 4 request pseudo headers. Now, those headers are mandatory, and it's a closed list. You cannot change them, you cannot add to them, you cannot make up your own. Each of them is starting with the colon, and their purpose is to replace the data which is transmitted over the HTTP start line. So we have one for the method, we have one for the path. The authority would replace the host header, which we had in HTTP 1. And the scheme would tell us if it's in HTTP, HTTPS, or FTP. The protocol supports not only HTTP transactions. If you'll notice, one thing is missing, and that's the version of the HTTP, which is no longer being sent in the new version of the protocol. So we have those, we have the client, and the client is establishing an H2 connection, and we've collected the settings frame and any other frame which is relevant up until the first request that it sends. And what we've noticed, that though this is a closed list of 4 headers, each client sends them in a different order. And this is consistent, I don't know why. And once again, you can see that Chrome is sending them different from the Go HTTP client or the Jetty HTTP2 client or Safari. And this is exactly what you're looking for when you're trying to passively fingerprint clients. Once again, this is a snapshot from the source code of Chrome. This is hard-coded. This is not some arbitrary decision that by some kind of a random dictionary that the Chrome is making on the fly. So now we have the final fingerprint. And we have the 4 elements which we've spoken about. We've encoded the headers, their initial letters, and we have the full fingerprint. And if you look at it, it's like a kind of a timeline where we know ideally if we could end the fingerprint at the settings frame, that would be best, because at that would be the shortest time where we can fingerprint the client, and we wouldn't have to wait for the first request. But you have a trade-off between the time that you are trying to wait until you're done with the fingerprint, which makes it a bit more complex. But I think that these take 10 seconds. I mean, a client would not initiate an HTTP connection if it does not intend to send a request. That would usually be the case. So I think that is good enough. So what kinds of use cases do we have for these fingerprints? So the obvious one is, of course, positive security. We try to validate client assertion. If someone is trying to use the Go HTTP client to send a HTTP request and assert itself in the user agent as a Chrome 67, that if I have a good fingerprint directory, that would, obviously stand out. So we can both validate the assertions of real browsers, or detect impersonators. Another useful tool is for tool detection and forensics, maybe, if we can look at that in that way. And And the last but a very interesting point is that if you think about it, if we see an IP from which originating a large amount of fingerprints, especially of valid browsers, we can then try and make some assumptions about this IP. This could be a VPN exit node or some kind of an anonymous proxy, or this is a signal by itself, so that's very interesting. Now, I've added this last line to the comments, and I don't know if you are dealing in the attacker side or the defender side or forensic side, whatever. But whenever you are using fingerprinting, best results are obtained when you are combining fingerprints from different layers. Don't only do application layer fingerprinting. You have other layers in between and use them as much as you can. So what are my key takeaways for you? Hopefully by now you should have some basic good understanding of how HTTP 2 works. What are the key advantages of HTTP 2 over 1? What are the key elements, the flow, the key differences between HTTP 1 and 2? Hopefully by now you are aware of the fingerprinting capabilities of which data could be exposed about your client when you are using H2. And I gave you some initial concepts of how we can try and obfuscate that. And last but not least, the proposed fingerprints, the elements, which ones we chose to leave out, and some real-world examples and use cases. Questions? Yeah.
What is the mechanism for associating two frames to the same message? Because each frame only has the street number. It doesn't have the message number or message identifier.
Yeah, well, there's some kind of a logic, and the flags within the frame could indicate that. For example, the headers could be contained in more than one headers frame, and there's a flag which is called end headers. And if that flag is not set, then the application knows that it should expect another frame, which is called continuation frame, until it is meeting a frame with a flag. And so that would be all kinds of flags and mechanisms within the RFC but that's a good question. Thank you. Yeah. The question was would this something that would go away when browsers update themselves? Well, we've done that research for more than a year ago, early 2017, and browsers have kept on updating themselves, and we see no evident changes. And this is true especially for automation libraries, where we have software which is using all kinds of libraries for HTTP 2, and they don't always, update themselves and recompile with different libraries. So I think the fingerprint is quite sustainable, though, if there would be any changes introduced, you would see them. As long as you have visibility into the traffic, you would see the changes, which is fingerprint can be dynamic per version.
That's very interesting. The other question is, this is specific for the browser and the server. Like, can it be cross-browser or cross-server, cross-domain?
Yes, that's why I said you should combine several layers of fingerprinting. You don't get the best granularity when only relying on H2 fingerprint. You could still have clusters of different browsers using the same settings. By the way, since HTTP 2 is mostly over TLS, the most convenient way to observe the traffic is you have two ways. One of them is just install your own ng HTTPD server, and it has a very verbose and clear logs, as you've seen. And the second one is use Chrome net internals that would show you a complete verbal log of all the frames which are exchanged. So those are both endpoints of the conversation. You could set up Wireshark and some other stuff, but that would require some more effort to do so.
Awesome.
Cool. Yeah. We have that for some of the browsers, not for all of them. There are some browsers where it's impossible to distinguish between different versions, but some of them we can do that. Yeah. I think you can fingerprint anything. I mean, everything which has an expected, hard-coded, consistent behavior. Even the fact that someone is randomizing things is something that you can fingerprint. The fact that it's never coming with the same values or keep on randomizing. So you can fingerprint anything. That's a good direction to think about. Yeah. 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 Well, that's a good question, an interesting question. Well, what happens if within the same browser, on the same version, you turn to incognito mode, and the guy here was saying which the header order in HTTP 1.x is, we can observe them changing within the same version, the header order of the regular HTTP headers. And the truth is that I have not tested that, and now I'm very eager to see that. That's interesting. Yeah. Yeah, well, that's something that occupies us a lot, headless Chrome and all those headless browsers. It's not 100% effective. To distinguish them from real Chrome or H2 is not the place you should look at. Yeah.
Is it possible to transport your results onto encrypted connections? Or because when the settings are sent, there should be a lot of small packets first. Can you detect that even when encrypted?
Well, from a side channel, can you observe the encrypted traffic and know that this is a settings frame? I'm not sure I understood the question. Yeah?
Yeah, I think only when you have the encrypted traffic is it possible to gather some information about the client.
You have to be one of the endpoints, yes, unless it's going over clear text. But if it's over, I haven't tried that, but logic says that, yeah, you would have to be, aside to the conversation to actually fingerprint, or a proxy within, in the middle, to actually be able to do that over an encrypted channel. Yeah. Yeah, no changes.
No changes, the same.
Yeah.
That's what the second one is over proxy, because sometimes, especially in HTTP1, we see that sometimes proxy has been and today somebody is
Well, proxies can add headers or things like that, but the proxies that I've mentioned, which are for HTTP2, they don't do it. I'm talking about pure HTTP2 proxies, not proxies that do on the upstream HTTP2 and then translate it to HTTP1, which is not really the case. But for HTTP2 proxies, if you'd use, like, for example, MITM proxy, the server would not be able to see anything. MITM has its own fingerprint, his own way of setting up a TCP connection with the server, and the server would be completely blind to the things that your client, your browser is sending to the proxy.
So no change if you use some
No, not that I've noticed. Okay. Okay, thank you very much, guys. Thank you.